Now that we've distinguished between absolute and conditional convergence, let's talk about how you start an example and decide whether or not a series converges absolutely, converges conditionally, or diverges. Before I go into specific examples, I want to point out that there are a couple pathways you could follow in order to answer this question. So, in general, when I'm talking about these different types of convergence, there's two series in mind. There's the sum of the original series, a sub k, where the assumption there is that those terms could be positive or negative. And there's the other series, which is the sum of the absolute value of the terms. And let's put that there. So one way to start is to look at the original series. If you look at that series, you can use any of our tests that are valid to decide, does that series converge or diverge? And that's putting me in this diagram at the top here. If it diverges, then you can simply stop and the series diverges. There is no other kind of classification that we look at with divergence. If the original series converges, then basically you've ruled out, among those three possibilities, you've ruled out divergence, but we don't know if the series now converges conditionally or absolute. So then we have to follow up by looking at the sum of the absolute values of the terms. Once I look at that in conjunction with the original series, then either if the sum of the absolute value of the terms diverges, then we say that the original series converges conditionally. Or if the sum of the absolute value of the terms converges, we say that the original series converges absolutely. I'll say alternatively, you could have started by looking at the sum of the absolute value of the terms. Here, it's if you find that this series converges that you can stop without having to go further. If the sum of the absolute value of the terms converges, we automatically know that the original series converges absolutely. However, if this series diverges, the one with the absolute value of the terms, that rules out the possibility of the original series converging absolutely, but we still have to distinguish between divergence or conditional convergence. So in that case, we would follow up by looking at the sum of simply a sub k. If that sum also diverges, then that's what we're trying to answer to begin with. We say that that series diverges. If that sum converges, then we say that it, in fact, converges conditionally. A key thing to point out is that if a series is conditionally convergent, no matter which of these paths we choose, you're going to have to test both series. So if I find conditional convergence here, notice that that path would require me to go along two legs of it. And if I find conditional convergence here, same thing happens. If you suspect that the series is divergent, then my first pathway here is what makes more sense, because you would only have to check one thing. If you suspect that the original series converges absolutely, then it would be nice to start with the sum of the absolute value of the terms, because that only requires one check. But I'll also point out that you shouldn't stress too much. You might look at a series and have no idea, no intuition about whether or not it converges absolutely or conditionally or diverges. And so just take comfort in the fact that regardless of which one you start with, you can get to the final answer. So it doesn't matter if you don't have an intuition about which of these should be better. So that's just something I want to kind of keep in mind. So that gives us our framework. Let's look at some particular examples where I'm going to be thinking about those pathways above. So to begin with, if we look at the sum from k equals 1 to infinity of negative 3 to the k over 4 to the k times k. So the goal here is to decide, does this series converge absolutely, converge conditionally, or diverge? Now, it turns out for this, I'm going to point out that there are several approaches. So I want to go through several different ways we could tackle this. And I'll number these just to distinguish. So approach 1. Let's start by looking at a sub k. So I'm distinguishing between my two paths up here. Now, if we do this, one thing that I might observe here is that this series is certainly alternating. So if I wanted to decide if this series converges or not, I'll try the alternating series test. Now, remember with the alternating series test, we look at, so this is a sub k, the absolute value of a sub k. Importantly, maybe let's look at this first. The absolute value of negative 3 to the k over 4 to the k. Importantly, I know that k here is positive because it ranges from 1 to infinity. Because I'm thinking about the fact that negative 3 to the k is negative 1 to the k times 3 to the k, taking the absolute value leaves me with 3 to the k over 4 to the k times k. And maybe better than that, I can write this as 3/4 to the k divided by k. We'll see that that'll make it a little bit easier to analyze. So recall that with the alternating series test, we ignore the sign portion of our terms, which means I'm ignoring this negative 1 to the k. And I want to verify that the limit as k approaches infinity of my terms is 0. Notice that the numerator is shrinking to 0 at the same time that k is going to infinity, so this is certainly going to be true. The other thing to think of here in checking that my terms are decreasing, I want to make sure that 3/4 to the k plus 1 divided by k plus 1 is smaller than 3/4 to the k over k. Again, that's certainly going to be true. The denominator on the left is larger at the same time that the numerator on the left is smaller. So both of these hold, and what that tells me is that the original sum converges by the alternating series test. Now, the question that we haven't answered, though, is it conditional or absolute convergence? And I'll point out here that the question, of course, matters. So, of course, I didn't write the question. So what I said here with the example, what we were trying to do is, suppose we were asked to decide among those three possibilities: absolute convergence, conditional convergence, or divergence. If the question simply said, does this series converge or diverge, we'd be done here. But assuming that we have to further clarify that, then we need to look at the series, which is the sum of the absolute value of the terms, which we've already established what that absolute value looks like. That's 3/4 to the k over k. Now, we want to decide if that series converges or not. What I'm going to look at here is the knowledge that that series, so looking maybe more at it in this form, look at how that is related to the series with terms 3/4 to the k. So it's easier, like I said, to note that comparison with the box representation up here. If I simply remove the k from the denominator, I'm going to get a larger series. This series, 3/4 to the k being the terms, this converges. We'd have to say why. It's because it's geometric, and the absolute value of r is 3/4, which is strictly less than 1. So that means that the sum of the absolute value of a sub k converges by the comparison test. So notice that there's a lot of work involved here, at least with this approach. We had to reference everything that we're using. So with the original series, we had to check both of our conditions of the alternating series test and make sure we reference that. And then with the second part where we looked at the sum of the absolute value of the terms, that required us referencing a converging geometric series and the comparison test. So our work really requires all of these justifications, and without that, this approach would not be complete. So from these two pieces together, we found that both the sum of a sub k as well as the sum of the absolute value of a sub k converges. So putting that together, I say that the original series, whoops, this should be a 3, converges absolutely. And my justification is everything that came previously. So of course, this is a complete solution, but part of what I want to accomplish in this video is to provide you with alternatives. So how else could we have approached this same example? I'll call this approach 2. And in the first approach, we started by looking at the original series. So something else we could have done here is start by looking at the sum of the absolute value of the terms. Essentially, what we did here. So kind of skipping the work with the alternating series test. If we had started by looking at the sum of the absolute value of the terms, once we show that this series, the one with the absolute value of the terms, once we show that that series converges, so we'd still have to reference the geometric series and the comparison test, but we'd simply be able to say that the sum without the absolute value converges absolutely. And here, importantly, we'd have to reference the absolute convergence theorem. So that would be a little bit less work because we really only had to work with the sum of the absolute value of the terms and simply throw in that extra statement about the absolute convergence theorem. That would be a complete solution. And then finally, something we haven't really considered is that I could look at this series using the ratio test. So if you'll remember, the ratio test did not require that the series we're looking at have positive terms. So that makes it less restrictive in terms of its assumptions, like the comparison test, limit comparison, or integral. So what we look at in the ratio test is we look at the limit as k approaches infinity, importantly, of the absolute value of the k plus first term divided by the kth term, which I'm going to represent as multiplying by the reciprocal of the kth term. So we want to find this limit. As I go through this, a couple things I can observe looking at the like terms. So notice I'm going to have an extra factor of -3 in the top and an extra factor of 4 in the bottom. Now, because of the absolute value, I'm going to represent that as just 3/4 instead of having a -3. What's left is k over k plus 1. I don't need the absolute values on that because k is positive. So this limit, because the limit of k over k plus 1 as k approaches infinity is 1, we get 3/4. Now, in order to make a conclusion, let's recall that the ratio test says take that limit, compare it to 1. This is strictly less than 1, so the series converges by the ratio test. Now, what I haven't specified, but I'll say now, is if you ever show that a series converges by the ratio test, it automatically converges absolutely. So I'll say that our conclusion here, as we found in the other two approaches, we say that this converges absolutely by the ratio test. And that's a complete solution. So, like I said, in general, if you find that a series converges using the ratio test, that's automatically absolute convergence. And you can think about that as related back to the fact that you're taking the absolute value within that limit. So, as a consequence of this, of course, we might think, why don't we just use this all the time? Any series that converges conditionally is going to be something that you either wouldn't be able to find that limit, or you'd get a limit of 1 where the ratio test is inconclusive. So that's why we have to have these other approaches as well. Okay, so like I said, that's lots of different paths. And I want to look at just one more example to make sure this process is clear. And again, for this, I'm not going to go through a bunch of different approaches, but I will again say that I'm not saying there's only one correct pathway through this. Same general goal. We want to decide on whether or not a series converges absolutely, conditionally, or diverges. But now let's look at one whose terms are negative 1 to the k over 1 plus the square root of k. Somewhat arbitrarily, I am going to start with just looking at the original series here. I note that it's alternating, so I check my conditions, which are that the limit of 1 over 1 plus root k is 0. As k goes to infinity, I see that that's true. And also 1 over 1 plus root k plus 1 is smaller than 1 over 1 plus root k. See, that denominator on the left is larger, so this is also true. So both of these hold. So that tells me that the original series must converge. The question is, yet again, is it conditional convergence or absolute? And that requires me to look at the next part here. So I've got this series. Now notice that in taking the absolute value, oops, I didn't finish my statement above, this converges. So now we're looking at this series. This is the sum of 1 over 1 plus root k. So if I'm looking at this series, which has all positive terms, the thing that jumps out to me is the fact that this reminds me of a p-series. And the p-series it reminds me of is 1 over square root of k, which is 1 over k to the 1/2. Now, in looking at these, the relationship is that the p-series is larger because we can compare those denominators there. Notice that this direction, while true, means that comparison test is not useful because we are bounding our series above by one that diverges. But it's exactly in this instance that I want to move to the limit comparison test, where I have these two same series as the ones playing the role of the sum of a sub k and b sub k in my LCT statement. So the limit comparison test requires that we take the ratio of one of the series general terms divided by the other and consider what happens as we send k to infinity. This becomes the limit of root k over 1 plus root k. This is the same thing if I divide top and bottom by the square root of k as this limit. And as k goes to infinity, notice that this 1 over root k will go to 0. So we're going to get 1 for this limit. So again, it can be confusing, all of the different kinds of limit results that we might get with test. This is not the ratio test. So 1 is not a problem here. It's the limit comparison test. All we care about is that the limit we get is not 0 and it's not infinity. And certainly we've satisfied that here. Once I've established that, all that means is that my two series behave the same. So we say that because the sum of 1 over root k diverges, again, that's because it's a p series with p 1/2, which is less than or equal to 1. Because that's true, we know that the sum of 1 over 1 plus root k diverges as well, and I have to reference LCT. So all told, the original series converges, the sum of the absolute values of the terms diverges. So putting those two together, that's exactly what conditional convergence means. So my final answer here is that the original series that had both positive and negative terms converges conditionally.